so car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Both are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? Okay, like most of these, if you're just reading it and trying to write down an answer, it is very confusing. So what do you think we should do first? Draw a picture. All right, so we have our two cars. I know that car A is traveling west. So let's say this is where car A is starting, and it's going west. Okay. Car B is traveling north. So, and we're looking for the point where they meet each other. So car B has to be down here, going north so that the two would intersect at some point. All right. At what rate are the cars approaching each other? So how would I show the distance between the two cars? Okay, let's label these sides. Since this is the distance car A is traveling, I'm going to call that A. I'm going to call this side B, and I'll say C is the distance between each other. Okay, so if car A is going 50 miles per hour, anytime I see a rate, I know it's the derivative. It's how A is traveling, so that's the derivative of A. So dA dt is 50. Car B is going 60 miles per hour, so that means dB dt is 60. I want the rate. When you see rate, what am I asking for? A derivative. The rate the cars are approaching each other. So I need the derivative of the distance from each other. So I'm looking for dc dt. When car A is 0.3 miles and car B is 0.4 miles from the intersection. What is the 0.3? And B is 0.4. So that's my picture and everything I was given. Are we okay with that part? So, what formula would we use? A squared plus B squared equals C squared. Is anything constant in this one? Which piece? So constant would be like anything that doesn't change. So our last problem we did yesterday, we had a ladder, and the length of the ladder wasn't changing. Are any of these sides staying the same? Well, that's just at that one particular instant. So you're right, those are constants at that instant, but can I plug them in yet? No, because overall the side is changing. So I'm not plugging in anything before my derivative. We just do the derivative of each piece. So we have 2a dA dt plus 2b dB dt equals 2c dc dt. Okay, so if I plug in, I know my a, I know my dA dt, B dB dt. Okay, I don't know C, and dC dt is the thing I'm trying to find. So I need to figure out what C is. How would we do that? Yeah. The particular instant we know these sides are 0.3 and 0.4. So we could find the C at that instant. 0.25 equals c squared. So c at that instant is 0.5. Okay. 48 equals 2 times 0.5 is 1 dc dt. So dc dt is 78. What would my units be? C was my distance, which is measured in miles. T is my time, which was in hours. How's that? So good labeling is very, very important here. Picture is very helpful. I really, really want you to make sure that you are writing out like all the stuff that we have. Okay, that's where people make mistakes when they try to skip some of those steps and then they plug things in the wrong spot. Okay. Let's take a look at this one. Why don't you guys take a second, read it, and see what you can set up. String. The kite is 120 feet above the ground, and the wind is blowing the kite horizontally away from her at 6 feet per second. I saw everybody had a triangle drawn, so I think that's the right thing. We've got the girl down here. The kite is being blown away. Here's my kite. Okay, and she is holding on to the string. Are you okay with that part? So I saw two different options. Like some people had all of these sides as variables. Some people had some of them as numbers. So let's just make sure any numbers that I put in now have to be constants. So if the wind is blowing the kite away from her, is this side changing? Yes. So that has to be a variable. Okay, I don't care what letter you call it, but it has to be a variable. At what rate must she let out the string? So as it's blowing away from her, it needs more string. So is this side changing? Yes, so that has to be a variable. I don't care what you call it, but it has to be a variable. If the kite is just blowing horizontally, is the height above the ground changing? No. So we could go ahead and just say this is 120 because we know it's not going to change. And any numbers like that that we could put in at the beginning will just help us later on. Now, if you call it a variable for now, you'll have to adjust later on. It doesn't mean you're wrong, it just means later on we change it. Okay, so it's going away from her at 6 feet per second. So what would that be? Dx dt is 6. At what rate must she let out the string? Y is my string, so I need the rate, so we're looking for dy dt. When 130 feet of string has been let out, what does that represent? Y. Is Y always 130? No, because she keeps letting out more string. So I can't plug it in yet, but at some point I will. So then, triangles, we do Pythagorean theorem. This would be the point when you go to do the derivative that if you had called that 120 a variable, when you did the derivative, since it's not changing, it just becomes 0. So the derivative of 120 squared is 0. Dy dt. Okay, once again, I have some of this stuff I'm looking for dy dt, so I have to figure out what x is, but we've seen this quite a few times. We need x at the instant when the y is 130. So we can solve it. X squared plus 120 squared equals 130 squared. So x is 50 at that two coordinates. So if we divide 30 over 13, or you could give me a decimal. But, y was a distance, so that was feet per time, and this problem was in seconds. So 30 over 13 feet per second. Is that one okay? Let's do another one. Actually, I think I'm going to save this one for Monday. Let's go to example 9. I'm going to jump around a little bit. So we have a man, 6 feet tall, walks with a speed of 8 feet per second away from a streetlight that is atop an 18-foot pole. So I have my light pole here. Put a light on the top. And does the height of that change? No, so I can go ahead and say that's 18. And we have a man that's walking away from the pole. And I know my man is 6 feet tall. Okay, and that's not changing, so I can go ahead and call that 6. How fast is the tip of his shadow moving along the ground when he is 100 feet from the light pole? All right, so we have to think a little bit here. Where does your shadow go? On the ground. Okay, that's the first thing. Somebody always tries to put it on the hypotenuse. Shadow's on the ground. All right, now next question. Now we really have to think. Where is his shadow? Is it behind him or in front of him? The light's going to be behind him, so his shadow would be here. That's what we're looking for. All right. We want to know how fast the tip of the shadow is moving on the ground. So we have a lot going on here, don't we? We need to label some variables. If I make a triangle here, we really have a triangle within a triangle, don't we? This one is a little confusing because we have two different speeds. We're measuring the speed he is walking away from the street light. So this is where he started. If he's walking away, that has to be a variable. So x is just from here to here. All right, so then his speed, that would be dx dt, is 8. All right. tip of his shadow is all the way out here. So that's like this whole distance. So I'll have to make that a variable. So y. So if I'm talking about how fast the tip of the shadow is moving along the ground, I am looking for dy dt. When he is 100 feet from the light pole, what variable is that? All right. Any thoughts on what we might do here? Yeah.
Figure out, so we do a Pythagorean theorem and figure out that line on the one side.
Okay.
So,
If we can get something along, or some kind of variable or unit for this side, we could do Pythagorean theorem. Did I give you any numbers that we could use there? No. If I call it C, is it constant or is it changing? It's changing, but I don't know a C, I don't know a dc dt, so that's going to introduce a lot of variables that I don't have any values for. So it's an option, but it's a problem, because I don't give you that information.
I was thinking, so a little triangle like this one,
Yeah, the little triangle.
like this one. Because we have an 8 and a 6, and that's 12. And we know that x is 100. So we can figure out this, but I don't know how that helps us.
You're right, so we could get a formula for that part of the hypotenuse.
Yeah, but I don't know.
But you still have the other piece.
And would that help us on? Wait, if we got those, I don't know. Let me this one, because we have 12 feet and 100 feet, but we can figure out this one. Yeah.
We really have two triangles here, don't we? We have the big one, the height of that is 18. The bottom of that is y. And then we have this little triangle in the tip. The height of that is 6. What would this length be?
Y minus x.
The whole thing is y and x is from here to here. Wouldn't these be similar triangles? Both are right triangles, they share this angle. In similar triangles, remember you can set up a proportion. That might be helpful because then I don't have to have any new variables. I can just use the variables I already have. So you could say like 18 over y equals 6 over y minus x. Now, I don't know about you, I'm not real anxious to do the derivative of that mess. What could I do before I do my derivative? What if we clean it up a little bit? So 6y equal 18 times the y minus x. Okay, we could even do a little more. If I brought my 18x over here and subtracted my 6y over, now I have 18x equals 12y. And that's something that's very easy to work with. So if I did the derivative here, what would I get?
18 dx dt.
Equal.
Dy dt.
Dx dt is 8. I'm looking for dy dt. I don't even have to plug in the 100 that I was given. There's no way to use it. So if I divide over my 12, I get 12. 18 times 8 is 144 divided by 12 is 12. What would my units be? Y is in feet, time is in seconds. So it's moving away 12 feet per second. All right. Any questions there? Let's stop for today. Let's work on homework and ask questions.